Hello everyone, afternoon. This is my third and final session on the TYC lecture course. So as always, I think we'll start the discussion today by just asking if anyone has any questions about the material that was covered this week or the previous weeks.
I have a question related to the density mixing alternatives that you can use when doing the DFT. Because the more advanced methods, supposedly they store like previous densities, right?
Yeah, that's for most density mixing algorithms.
Yeah,
they store a kind of history of.
Yeah, but my question is, how many density do they store? Because what I thought when I read about that is that if you have a lot of iterations, you will have to start storing like a lot of the density distributions. So how do the programs manage to do that?
Yeah, well, this is something that almost always is a flag in a DFT code that you can fiddle around with and change. Something like 10 or 20 is quite usual.
Okay.
I mean, normally the density storage requirements are not so great because you only need to store the density, which is not one of the larger things in memory. So, especially as we discuss in these slide deck as well, like for most DFT calculations, if you're using hybrid exchange, that will be by far the largest part of the memory storage. And that wouldn't be affected by how many density snapshots you save up. So.
Okay, so it's not that expensive to store.
Yeah, most of the time.
Oh yeah, okay.
Yeah, if you're using a very large simulation cell with local functionals, then you might need to worry about that. In this case, you probably can shave some memory usage off if you reduce the number of snapshots you save.
Okay.
Yeah, I think pretty much every DFT code will kind of give you the option of changing that.
Okay, makes sense. Okay, thank you.
Any other questions today? No, okay, well, seeing it doesn't seem that there are, I'll share the slides again and we can see how that's covered. So, okay, share screen. Okay, can you see my screen now?
Yes, we can.
Okay, good. So the first the first topic that was covered was just talking about practically how you can do FCF convergence, how you can get these calculations to work. So SCF is just the acronym for self-consistent field, which is the sort of equations you normally need to solve in DFT when you're calculating the electron density for a particular system. And that's just because solving the actual Kohn-Sham equation, so we've got that here as expression 1 is a chicken and the egg problem. In that, you need to know the electron density to calculate things like the Hartree potential. But then when you have that Hartree potential contribution added in, it will change what the density actually is. So the solution to solve these problems normally is just to take a guess at the density matrix. If it's a better guess, it will make life easier, but you generally speaking guess what the electron density should be, and then use that electron density to calculate all of the energy terms, such as the Hartree interaction, and then solve the equation that you've just generated to get a new density matrix. So if the guess you had was the actual electron densities, the actual solution of the Kohn-Sham equations for your system, your initial input density and your output density will be the same thing. And in that case, you've got the right solution to the Kohn-Sham equation. But normally what happens is when you run this procedure, you'll get a different density out than the one you put in. And what we do is we kind of take this output density and we can run the procedure again. And that's the basic idea of how SCF calculations work. So I've got a flow chart on this slide that kind of takes you through that process. If you have a density, then you can construct the Hamiltonian, calculate all the energy terms, including this Hartree interaction with that density. You can solve the quantum equations for that in that potential. And then you can look at how much the energy has changed between your input and output density. And if the difference is very small, that means that your density is very close to what the solution of the equation should be. And normally then, if it's below a certain tolerance, you'll take that as the answer, the density you wanted to find. But if not, you'll use some sort of density mixing to mix together these new and old density matrices. And just repeat this process until the density stops changing. The simplest way you could do that is just to take half the input and half the output density, add them together, times it by half, and that is your new input density. I just thought this has been something that will work well in simple cases. So here's an example of convergence of just a 2x2x2 supercell of magnesium oxide, which is a nice clean system with a reasonable band gap. You can see that if we keep on doing this, then the density, the changes in these input and output densities get smaller and smaller, so we can achieve any tolerance that we want. But this doesn't work very well in a lot of practical, more complicated calculations we'd want to do. And the problem is often called, one of the main problems you get is this problem of charge sloshing, which is basically wherever the electron density goes in the system, it will repel other electron densities from those regions. So what happens very easily is that you run one step, all the electrons rush to where there's no electrons. And they move, say, to the left of your system, and then you run a second iteration, and they just go back to the right, because there's now no electrons there, and that's where they want to be. So you very often end up with solutions like that, where when you are mixing these densities together, your electrons just moving from one side of the system to the other. It's so-called charge sloshing instability, and you just don't get anywhere. So on this slide, I've shown an example of using this algorithm for when there's a defect in magnesium oxide. The defect state makes the situation a bit more complicated. You see that this direct mixing of the densities doesn't work. You just get stuck without any change in the convergence. So as I say, what's happening is that the input and the output density is swapping places every time we run this algorithm. So we don't make any forward progress. We're just going backwards and forth between two solutions, two densities that aren't a solution of the equation. So practically what is done in these calculations is using a more complicated way of mixing together past densities. I do just highlight Broyden and Perlet mixing are the most common things that you'll see, and they both work quite well. They're both fairly complicated algorithms, but ones that are quite well established. And in both these methods, what you do is you keep a history of the density matrices that are generated through this procedure, and you're just mixing together certain fractions of these densities in a way that's designed to try and avoid these charge sloshing problems. So for this example of this oxygen defect, using Broyden mixing, you can see that it resolves this problem in terms of charge sloshing. But there also are problems whenever you have unoccupied levels near the Fermi level in convergence. And this means that it also can be quite hard to converge solutions to these quantum equations for metallic systems. When your system's metallic, there's always going to be a lot of states that are just above the Fermi level and completely empty, and a lot of states that are just below the Fermi level and completely occupied. So when you're performing this density mixing, states are continuously moving above and below the Fermi level and changing their occupation completely. This can make things quite unstable as well. The normal solution to these problems is to apply a smearing temperature to the calculations. So rather than having a step function in occupation at the Fermi level, you smear it out with a thermal distribution function. I think it's just important to stress when we're using temperature in this way that this temperature isn't a physical temperature. It's just a kind of computational tool that we're using. If you want to do DFT properly for temperature, you need to also allow movement of the atoms. So in this situation, we're just treating temperature of the electrons, but we're keeping the atoms at 0 Kelvin. You want to do DFT properly for temperature, it's important to allow thermal energy to be placed in the atoms as well, rather than just the electrons. But when you're using this smearing trick, then you can take the energy as temperature tends to 0, the smearing temperature tends to 0, and that's the answer that we're looking for. So taking together these combinations of density mixing algorithms and temperature, smearing temperature, it's normally possible to converge the electron density for a wide range of systems of varying complexity. But whenever you have problems with converging FCF, then it is worth thinking about these two things. It's worth fiddling around with the density mixing algorithms and fixing around with the smearing algorithm, which you might not be using by default, depending on the code you use. But, especially these density mixing algorithms, there are always a few parameters that you can fiddle around with and try and get convergence. Normally things like making the history longer so it takes more densities in, and telling it to put less of the new density into the new density is normally parameters that control that. Once we've succeeded in converging the electron density, then we can do a geometry optimization on top of that. So with this electron density, we can calculate what the forces are on all the atoms in the system, and we can try and move these atoms to minimize those forces and hence minimize the energy of the total system. The easiest examples to think about are situations where there's essentially only one distance involved. The easiest thing for that is to look at a diatomic molecule. So in this example here, I just have a sodium atom and a chlorine atom. So the only structural parameter that you have when you have just these two atoms is the separation between them, how close the two atoms are sitting to each other. So just using density calculations, what we can do is we can pick different values of separation between the sodium and chlorine ion and calculate the total energy. That'll give you something like this blue curve, which is a very common sort of curve to see for any sort of molecular bonding situation. It's a bit like a Buckingham potential, if you have seen those in the molecular dynamics context. But when the two atoms are quite far apart, they don't really interact with each other. As they get closer to each other, they start to become attracted to each other and want to form a chemical bond of some sort. In this case, it's quite an ionic situation. So one of the electrons wants to transfer from the sodium to the chloride. And then as you try and push these two atoms to even closer together, then they'll start to repel. The electronic wave functions will start to overlap too much and you get quite a strong repulsion. So this sort of curve is basically what you often see in chemical bonding. You've got this very repulsive regime where things are being pushed too close together and you're starting to get wave function overlap. And you have some equilibrium distance, that is the bonding distance for that particular system. So this green diamond here is just where if you run a geometry optimization on this situation. So it will try and calculate the forces of these two atoms and find the positions of these atoms that minimize the forces. So you can see that geometry optimization, given an input structure, will take us to the equilibrium separation here that these two atoms want to have. But
I have a question with that. Can you map those results from the geometry optimization to a potential like Leonard-Jones or something like that?
Definitely you can, yeah. So yeah, I mean, if you wanted to fit a Leonard-Jones potential to sodium and chloride,
I just use Leonard-Jones as an example.
Yeah. So this is something that's very commonly done.
Okay.
A lot of molecular dynamics force fields are produced by fitting to DFT data. As always, the potential will describe what you fit it to most of the time. So we wouldn't expect if we fitted an MD force field to this curve that it would reproduce everything to do with sodium and chloride interactions, but it would produce the right separation of this dimer.
Yeah.
But the important thing to always realize, so I'll stress this because this is a very important thing, is that when we run geometry optimizations in DFT, we're not going to find the global minimum structure, we're just going to find a local minimum. So if we put all our atoms in a DFT cell and we perform a geometry optimization, we shouldn't expect that the result of this geometry optimization will be the lowest possible energy configuration for those atoms. It's only going to be a low energy configuration near to where we started. So if we started off a calculation here, say, it would find its way to this local minimum, and then the forces will be 0 and the geometry optimization will stop. We can't normally expect that the geometry optimizer will climb over this barrier and find this actual lower energy configuration for us. So just running a geometry optimization isn't going to tell us what the lowest energy structure should be. Just as an example, I used carbon here. On this slide here, we've got 6 different allotropes of carbon. Carbon is one element that can actually be stable in quite a lot of different structures. For instance, you've got things like fullerene, where you make like a giant football basically out of carbon atoms that's quite stable. You can roll carbon sheets up into nanotubes, or you can just have individual carbon sheets as graphene. Materials that have a lot of technological interest in them these days. But the lowest energy configuration of carbon atoms, if you just have carbon, is actually this diamond structure. Though graphite is quite similar in stability. In diamonds, you have tetrahedra of carbon atoms. It produces a very strong structure. But if we put carbon atoms in a DFT cell and perform a geometry optimization, we're going to find a low energy structure similar to where we start. If we put in the unit cell of graphite and run a geopt, it's going to get the graphite structure back. It's not going to find its way to this low energy diamond structure. These allotropes are kind of an extreme example of that, but this is always something we've got to be mindful of in DFT calculations. Like if our initial guess of the geometry is quite far from the real situation, we can't expect necessarily that we'll find our way to it. There's lots of other examples you could use, for instance. Like if you take, for instance, the surface of a silicon crystal and you cut off a plane to make the 1-1-1 surface, then what happens in reality is that the surface layer completely reconstructs into a completely new symmetry at the interface. And things like that, you wouldn't expect DFT to tell you straight away. Like even if you did use a large unit cell, it probably won't find its way to that reconstruction that really happens. So ultimately, the test of whether we found the lowest energy structure is kind of frustrating from a practical perspective, but the simple truth is if you find a structure and it's lower in energy, then that is a more stable structure. But until you find, you can't try everything, so it's always hard to be sure if you found the most low energy structure that can exist. And if you're looking at a higher energy structure, then you can draw the wrong conclusions about what's happening. Anyway, the final part in these slides is discussing a really important topic, and that's the topic of exchange correlation functionals. So in terms of DFT calculations, the exchange correlation functional that we use is one of the main approximations we make. Although in principle there is, at least mathematically speaking, there should be a universal exchange correlation functional that describes everything well. We don't know that. We only know approximate exchange correlation functionals that work better or worse in different situations. So a lot of the time when DFT fails to reproduce reality, it's not an intrinsic failure of the idea of DFT, but the problem is that our functionals are not up to the task, not up to describing the situation we're asking for information about. And this, when we come to this topic of exchange correlation functionals, it's often described as being basically a ladder, where we start off on this bottom rung of the local density approximation, or here it's labeled LSDA because it's the local spin density approximation. There's always a bit of extra maths involved in evolving electron spin in DFT, So not, I think in most of the results here, I'm just discussing spin unpolarized DFT, but all of these functionals have generalizations to spin, which are well known, but just make the maths more complicated. The idea is as we climb this ladder, then we involve more ingredients in our exchange correlation functional, which makes it, computationally speaking, more expensive to run the calculation. And the hope is that as we increase the computational cost we're willing to pay and increase the amount of ingredients we're willing to fold in, that we can reproduce the correct situation more accurately. But of course, it's always possible that when we try and make more complicated approximations, they work out worse in practice. But yeah, this lowest rung is local density approximation rung. The only information that's used everywhere is the local electron density. So the LGA is very cheap. Then we have generalized gradient approximations as the next rung up, where we're willing to look at also the derivative of the electron density, the local gradient. Then we have the meta GGAs, which is, we allow the electron density. So that's basically the same thing as the second derivative of the electron density, del squared n, which corresponds to the kinetic energy. Then we can go up to what's sometimes called hyper GGAs or hybrid functionals, where we include some measure of exact Hartree-Fock exchange. And then there are even more sophisticated methods based on unoccupied orbitals, such as the random phase approximation. Yeah, the LGA is, as I say, is the simplest kind of practical approximation in DFT. And it's the only rung of this ladder that doesn't really include any empirical parameters. So essentially, practically speaking, there is basically just one local density approximation. Unlike all these other rungs of the ladders, there's not multiple choices of functional there. There are some slightly different parameterizations based on how these parameters are being extracted, but practically there's not much difference. You struggle to see the difference between these different fits that have been produced to LDA data. And the LDA is based on this, just approximating the exchange correlation energy as what, at each point, as what the exchange correlation energy would be of a homogeneous electron gas. So in many ways, what's surprising about the LDA is it works quite well a lot of the time, because any realistic system doesn't look much like an electron gas. There's always going to be concentrations and depletions of electron charge around all over the place. So this expression here, expression 5, is actually the exchange energy in the LGA, which you can see is a density functional. It just depends directly on the electron density n at each point. There are some expressions for the correlation energy here. Despite I say there is some like numerical choice of how you pack things up, but it's essentially the same thing. It's because there's different expressions people have fitted to the available results here to reproduce the correlation energy, and it's definitely messianic, but in practice it's describing the same curve. So these blue points here are some fairly old now quantum Monte Carlo simulations of a homogeneous electron gas that were performed in the 1980s, which were pretty accurate. And then these different lines are different fits that people have fitted to this data, producing the different colored lines. So your DFT code will use probably one of these fits to generate the correlation energy. But practically, it's hard to see much difference between the various ones that have been produced. We want to make more sophisticated approximations. Then we start having to introduce empirical parameters to some extent, where we can make different choices. And now we have families of approximations rather than just one. So the next step up is these generalized gradient approximations, where it's a functional not just of the local density, but the local derivative of the density. I think the most popular GGAs are PBE, PW91, and BLIP, or there are others. These ones are quite well established. To use a GGA over an LGA doesn't cost you much more in terms of computer time. But as I say, there's more available choices of these parameters. People are generally quite happy with PBE these days. in terms of, well, happy might be the wrong word, but people have generally kind of think that it's not really possible to make PBE much better than it is in a general purpose way. So in terms of the different GGAs that are available, there are GGAs that are better at certain things, but it always comes at the cost of accuracy in other areas. And there isn't at the moment, as I say, much hope of producing a general purpose GGA that's much better than PBE. Although people have put a lot of effort into trying. So PBE is from 1996. That's essentially what I'm saying. In the past 20, 25 years, no one's really succeeded in making a GGA that's much better than, because clearly an improvement on PBE, generally speaking. So this kind of forces us to try and do more expensive things. You're following this recipe of this Jacob's ladder that I had on the previous slide, and the next thing to try is meta GGAs. So examples would be the TPSS functional, the scan functional, MO6L, things like this. Again, this meta GGA is not that much more expensive than GGAs. So in principle, they're quite attractive for that reason. But meta GGAs haven't been used as much because it's been really hard to produce a good meta GGA practically. So people have produced meta GGAs, but they don't tend to be very transferable. They don't tend to work very reliably for different situations. I think it's fair to say that some of these newer iterations, things scanners from 2015, for instance, are looking like they might be a bit better than some of the past meta GGAs. But still, meta GGAs are not used loads at the moment. So it's like, even though there does seem to be a clear route to using this second derivative and the kinetic energy to make better approximations, people have struggled a lot to produce good approximations in this way. This leads us then to this hybrid functionals where we mix in some amount of exact exchange from Hartree Fock. So popular examples would be PB0, B3LIP, and HSE, although there are many others. But the important thing to realize is that using a hybrid functional is really, really a lot more expensive than anything else we've been talking about so far today. It really does increase the cost of your DFT calculation a whole lot. So for that reason, that is a downside of hybrid functionals. They're always going to reduce the size of the system we can consider. But the upside, I guess, is that these functionals can be more accurate. Otherwise, people wouldn't use them. But there is an important choice in terms of how much of this non-local exchange we should include in our calculation. And there are also important differences in the way these functionals treat exchange at short and long ranges. Originally, hybrid functionals started out as kind of someone had kind of sort of realized that if you mix these things together, you get better results. And there wasn't a particularly deep understanding of how that was justified. So some guy basically realized, DFT underestimates all these properties, Hartree Fock overestimates all these properties. If we mix the two together, maybe that would be better. So that's what Axel Beck did when he invented hybrid functionals. At that point, it was a kind of intuitive idea. But it turned out that you could get very good results doing this. And that meant people became quite interested in trying to understand how that works, how mixing together these two different theories can be justified. And these days, I think it's fair to say that there are actually very good mathematical arguments of why this is actually a good idea, as opposed to just mixing together two different theories to blend them and get something in the middle. Normally justified through this formula called the adiabatic connection theorem, which we won't go into detail in here, but I've put a link if you want to read more about that. But the idea is basically that you can start off thinking about the Consham system as a non-interacting system, and the reality is a system where the electrons interact with their usual strength. And you can make a mathematical argument about how, as you increase the strength of interaction, you can go from one of these systems to the other, the so-called adiabatic connection. So I think these days hybrid functionals can be justified quite well. It's not just an empirical mixing of two different theories as it started out. but there's a lot of choice in how you parameterize these things. You can leave quite a wide range of results. So one strategy is something that is followed by B3LIP and many other functionals, is to start off with a big, huge set of experimental data that you've tabulated and then calculate with DFT, and try and pick your parameters such that you can match these data set, your predictions from theory and your experimental data as well as possible. So this is what they did with B3LIP, and they did this particularly for chemical data on lighter elements. But B3LIP is actually a combination of 1, 2, 3, 4, probably about 5 different functionals kind of fitted together in various ways. And fitted to reproduce, as I say, thermochemical data. So this is a very popular approximation, especially for chemical calculations, because the data this was fitted to is chemical reactions and things like that. So it's quite good at describing molecules, but it's not as good for solids as some other functionals. The other strategy is to just, rather than trying to fit things, is to just try and have a minimal amount of parameters that you control. And that's sort of the strategy that's taken by something like PBE0. PBE0 is just is all PBE correlation energy, 3/4 PBE exchange energy, and 1/4 Hartree-Fock exchange energy. So in comparison with something like B3LIP, there are less parameters there. This factor of a fourth is justified as kind of in some limit, kind of corresponding to multiplicit perturbation theory. And this functional is quite popular in condensed matter. So I think between B3LIP and PBE0, B3LIP is better at describing molecules, and PBE0 is better at describing solids, although there are exceptions, just as a general comment. It actually turns out, though, that to do hybrid functionals for bulk systems is more challenging numerically than to do it for molecules, because of their need to do k-point sampling. Things like PBE0 don't play that nicely with k-points. So this has led to approximations like HSE, where you kind of dampen off the long-range exchange. This just makes the method much more stable. So this is the expression here for HSE, where basically if you pick this parameter omega even to be 0, it just is PBE0. But instead what's being done is that this long range exchange is being damped out from Hartree-Fock and just returning to PBE level at long range. I mean, I've got a few slides of different comparisons. There's always a few comparisons you can look at. But generally speaking, what we find is that LDA is good, but it's not perfect. So if this A0 column here is for lattice constants, and this is the mean absolute error, you can see that LGA has got quite a large mean absolute error compared to the other functionals. Going up to PBE level, so going up to this GGA rung, improves things a bit, but it's not a huge improvement. This depends a bit on what we're looking at. Generally speaking, LGA is better at metals. PBE is a bit more transferable to less metallic situations. Now, PBE Sol is a different parameterization of PBE that was fitted to be better at lattice constants. And that's what you see here. It's actually much better at describing the lattice constant of these materials. But if you jump down, this is what I'm trying to say about PBE being general purpose. You can see that PBE Sol is a lot worse at describing the cohesive energy now. That's what I mean. Like, always attempts, when people try and attempt to improve the PBE's description of something like, say, lattice constants, then it turns out it makes things like the cohesive energies worse. And it's found a GGA that is kind of better than PBE at everything at the same time. It tends to kind of be whatever you focus on improving, everything else gets worse. This TPSS functional is a meta GGA. And you can see here it's actually worse, a little bit worse than PB sol, but it's a little bit better than PBE for this this lattice separation. Lattice constant. And you can see here HSCO6, this hybrid functional, is the best at these lattice constants in the data set that this paper looked at. You see similar trends for the bulk moduli, how easy it is to deform the crystal, and for the binding energies here. So we are generally seeing improvement as we use hybrid functionals, but there's still errors there. It's still not perfect. This is a similar table from other paper which shows similar things. Yeah, you can compare some of these numbers yourself, but also does talk a little bit about what particular systems is better. One thing that hybrid functionals are much improved over local functionals is the description layer of band gap. So those tables were before about physical properties. So the main reason that hybrid functionals get used so much is they really do improve the comparison between theoretical and experimental band gaps. Because in local functionals we have what's called the band gap problem, where the band gaps get systematically underestimated by quite a lot, normally by about a factor of a half. You can see that the circles on this graph, which are the PBE results, are much lower than the band gap by kind of almost a factor of a half across this whole range of systems that have been considered. That these black squares for HSC are much closer to experimental band gaps. This is another comparison like in this paper here, where you can see that for a particular material, the different hybrid functionals will perform differently. So for some systems, PBE does better. For some systems, HSE does better. For some systems, B3-lip does better. So it's kind of frustrating in some sense, because there's a wide range of results for that you can get from the different hybrid functionals. It's not always clear what will perform better for the system you're interested in. But just talking in terms of general trends, you can see that none of these functionals are great, in that there's still kind of absolute errors of about up to 3 to 6 electron, 0.3 to 0.6 electron volts in these band gap energies, which is quite a big discrepancy still in experiment. And that overall, HSC seems to be the most accurate out of what they looked at in this study, and you can see a range of results. Part of this seems to be related to an argument that's been developed that the amount of exact exchange you should use is related to dielectric screening. So in molecules, you don't really have dielectric screening, and you need to use larger exchange fractions like are in B3-lip. But as your system has a higher and higher dielectric constant, as it screens external electric fields more strongly, then this seems to also screen the exact exchange and mean you should use less exact exchange. So this was a particular study where they looked at fixing the amount of exact exchange used in a PBE0 like functional to the dielectric constant of the material, and able to see some improvement. So it's kind of is useful in that there's some progress being made in understanding why hybrid functionals perform differently for different materials. This is also bad in the sense that dielectric is a property of a material, so you can't pick a fraction of exchange that's good for everything. Especially, this is a problem that comes up a lot. If your system has different subsystems in it with different dielectric constants, then at the moment you probably can't get a hybrid functional that describes both bits that well. If I had magnesium oxide, say, which is dielectric of 9, I can pick the amount of exact exchange that will reproduce magnesium oxide very well. But if I then interface it with another material with a different dielectric constant, then I can't pick the fraction of exchange for the dielectric constant of that material at the same time. So at the moment, hybrid functionals often are kind of tuned specifically to the material you have. And because of that tuning, you can't simultaneously tune different parts of the system at the same time. So there's still definitely room for improvement in the density functionals that we have, including hybrid functionals, but this is all a work in progress at the moment. Yes, I mean, in terms of the results, yeah, okay. This problem of this density mixing and smearing are important things if you can't to think about if you can't converge your electron density at all for whatever system you're interested in. Although also oftentimes, if you are having convergence issues, it could also be that your input structure is wrong. So I'd always recommend if you have a DFT calculation that's not working, the first thing you should do is try and visualize your simulation cell using a visualizer of some sort. I often use VMD, although it's a bit fiddly, just to check it looks right. Because at least half the time that I have a structure not working, it's because I put the input structure in wrong somehow. I've got Bose or angstrom mixed up or something. I've got the lattice constants wrong. So if you visualize it, you can quickly check if that's the problem. If that's not the problem, there are a couple of things you can fiddle with to try and improve the optimization. And this point, the second point that I made that I think is very important, is that when we do geometry optimization, we're going to find a nearby low energy structure, not the lowest energy structure that's possible. That's something that we always need to bear in mind. You can't expect DFT optimizers to take the atoms you put in the input and then find the lowest energy structure for them. They're just going to find their way to the nearest local minimum. You have these GGA approximations, which are very cheap computationally, so you can do, say, 2,000 atoms these days on a good supercomputer without too much trouble. But they tend to severely underestimate the band gap. And people are struggling to make more successful approximations using low-cost ingredients. And then we also do have things like hybrid functionals, or even more expensive things where we use unoccupied orbitals like the random phase approximation. But these make DFT much more expensive to do. So we're talking about, say, 300, 400 atoms on a good supercomputer these days, a big reduction in system size. But then we're struggling with this idea that we're no longer able to pick a functional that's good general purpose functional. We're finding that these hybrid functionals are quite system dependent. So there's a lot of room for progress in the future, and this is all developing as time goes on. But as things stand today, we don't have a good hybrid functional that you can use in all different situations. Anyway, that's the end of the slides I have here. Are there any questions on what I've just been discussing today, or just on exchange correlation functionals in general? I think one further point I can make is that local functionals are generally quite good at getting the structure correct, but the electronic structure in terms of things like band gaps is less reliably treated. Has anyone in this call been using hybrid functionals in their research? So that seems like a no. Has anyone been running DFT so far? Been doing some practical DFT calculations? Lots of raise their hands. So, what sort of calculations have you been doing?
Well, I run some bandwidth-based calculation using the PBE functional, and I also run some atomic orbital Bayer set calculation using the HSE level for HSE functional, and I think the time increase in for planar wave Bayer set when using the hybrid functional is terrible, and But for atomic orbital based set, I think it's okay because I run several tests on the PB functional and the HSE06, and at least for graphing, the the increase of the time consumption is, for me, it is acceptable. Yeah.
Yeah, no, that's a fair comment. I think there is a general point there in that it's easier to use hybrid functionals with local basis sets like atomic basis sets. So it's partly just because practically speaking, it's easier to use supercomputers for that sort of basis set. You'll see the problems of hybrid functionals being more expensive, much more severely if you're using things like plane wave basis sets that are completely delocalized across the whole system. So yeah, I think taken together, that's part of the reason why. And again, this point about k-point sampling being more difficult with hybrid functionals. It's easier to do hybrid functional calculations for molecules and for even for bulk systems, but where you use local basis sets. The challenge then is to have local basis sets that are sufficiently accurate for the situation we're looking at. What code was it you used to do those calculations, if you don't mind me asking?
For planar wave based set, I use the MASP, and for local based set, I use the crystal developed in my group, in my current group.
Yeah, I haven't used crystal myself, but that's one of the codes that is worked on quite hard to make it run fast on the supercomputers.
But I think we should be careful in choosing the proper base set, because sometimes it may produce very weird results compared with the planar wave base set.
Yeah, that's always the risk. With plane waves, you can at least either check if it's converged or see that it hasn't converged. With atomic basis sets, you have to put much more faith in whoever constructed your basis set that it does what you want. So there's advantages and disadvantages of the two approaches, for sure.
And for local base set, is just sounds not so ab initio. I mean, you predefine the shape of the orbitals.
Yeah. Yeah, I mean, yeah, exactly. I mean, that can be both good and bad, depending on how good the choices were. But yeah. And there's always this fact that with plane wave basis sets, even if they are more computationally demanding, you can always systematically improve them. Whereas for atomic basis sets, that it's much more possible to add in extra basis sets to make your calculations more expensive, but actually end up making the results worse. One of the main problems there is what's called basis set superposition error, which is not a problem in plane wave basis sets, but this is kind of an error that happens because you've increased the quality of your basis set and then makes your results worse, which is obviously not what we want. We always want to, if we're making our calculations more expensive, we want to see that cost we want to see improvements as a result, otherwise it's a waste of time, computationally of our time. But yeah, like I say, the flip side of that is if you are using atomic basis sets, then it is possible to run much larger scale hybrid calculations efficiently. So there's thriving communities using both of these approaches at the moment. You can't say that one is better than the other. Okay, well, unless there's any further questions, I guess we can leave it there for today. Yeah, it doesn't seem that there are, so let's leave it there. Okay, thanks, guys. This is my last lecture, so I'll be a new speaker next week.
Okay, thank you. Bye.
Bye.
Thank you.
Yeah.